Catheters are usually made of different polymer layers, and each polymer would have a specific job um, in a catheter structure. For these typical catheter, PTFE is used as a liner, and so is the inner layer of the catheter. And the reason for that is that the PTFE is very lubricious. It has one of the lowest friction coefficient among the polymer, and that will make it very easy for the guide wire to glide into the liner and make it very easy for the surgeon to operate when using the catheter. But PTFE is very inert, so it doesn't stick to other material and it will not adhere or bond with other polymers that we have. So we need first to etch the PTFE, and etching, basically with etching you are stripping some of those very stable fluorine bonds. So you remove the fluorine atoms, and what will happen is there are carbon radical on the surface that are very active. But these active carbon atoms, they can react with the oxygen or other material that are in the environment. So we use a primer, and the primer, what would do is that it would react some diisocyanate, like if you use a polyurethane based primer, it would add some diisocyanate group on the surface, so make the surface more reactive and creates functional group on the surface. This would enhance the bondability of PTFE. It would be more reactive and it could bond with other materials. After that, you need a braid, and a braid is a crosshatch wire structure that can be made from stainless steel or nitinol, and it would add kink resistance, torqueability to the catheter, and it would significantly improve the flex modulus of the catheter. After braid, you need an outer jacket. Outer jacket is usually made of material like PBAX, nylon, or polyurethane. And when the structure is heated up, this outer jacket can melt and would diffuse into the braid and would react with the primer, make the whole structure one. Um, to move the outer jacket better, more toward the primer, we use a layer called heat shrink, and that heat shrink layer is made of FEP. So FEP is a copolymer of PTFE and another polymer, that is polyhexafluoro polypropylene. So it has 6 fluorine group in it and 3 carbon. Addition of that segment into the PTFE to make it a copolymer, it changes the structure of PTFE completely. So PTFE it cannot melt. You cannot process it via melt extrusion. But FEP now, with the addition of that segment, is extrudable. You can extrude it, and if it's heated, it can melt. So when you extrude the FEP, you can use a process to expand the material, like 60% expansion radially, and then freeze that expansion. Basically, we set that expansion, and when you heat it up again in the secondary process, the material tends to contract and would apply a good hoop stress on the structure. So all these layers, they can diffuse together and bond together. We heat it up to a temperature that is below FAP melting point and is higher than nylon or PBAX melting points. All these layers are supported by a mandrel, that is a 3116 or another stainless steel or other material that is strong enough to act as a base, so it keeps the inner layer strong and fixed. What is the PTFE etching and why it is important? So as we mentioned, PTFE is very, very inert, and it will not stick to other material. And that's because of this chemical structure. So to be able to make it more reactive and adhere to other material, the first step is to etch the material. It's called etching, and it's basically is done with a solution of sodium naphthalate. An example would be sodium naphthalate in THF or other solvent. And what it would do is that it would strip the fluorine groups from the molecular chain. So removing the two fluorine groups, it will leave behind some transient radicals on carbon atoms, and those radicals are very reactive. They can react with other material, and then if you do primer, the primer would replace the fluorine. Basically, would react with the radical and put functional group there. If not, if you just leave the etch material in environment, it could react with the oxygen or moisture because they are very reactive. Also, the color would change when you etch it. You make it more like a brownish. In analytical polymers, what we do is that we can identify and quantify the etching, and we say, okay, this part is been 30%, 60%, or 100% etch versus a reference sample. Is primer needed for PTFE? We mentioned that when you etch the PTFE, basically you are stripping two fluorine group from the molecular chain. And so you leave behind two active radical carbon atoms there. Over time, these carbon atoms, they can react with the oxygen, and therefore the etching properties of PTFE could be affected. In most cases, a primer like a polyurethane-based primer would be used, and what it would do is that this functional group of the primer would react with that radical atom and basically create functional group on the surface of PTFE. So for this example, they are replaced with the diisocyanate functional group that are very reactive. And when the primer is applied, these groups are very reactive and would react with the outer jacket material, nylon or PBAX, and will create a strong bonding between the primer and outer jacket. So it's really depend on the bonding that you need. A strong bonding requires application of the primer. Why is braiding using catheters? Braiding is a metal wire structure that is using catheters, and the main function of braiding is that it improves the tensile modulus of the structure. For this example, you can see that the polyimide material, when it is braided, the modulus would increase significantly, almost 4 times. And that increase in modulus would increase the flexural stiffness, the pushability, and torqueability. We have explained how these 3 parameters, like a kink, torqueability, and pushability, are calculated in post number 43 in our web page. And of course, this braiding could have different shaping. I mean, going from distal to proximal, the structure could be different, and it's more related to the stress distribution, how the stress would be distributed when force is applied. And you can actually simulate that in a software to see how the stress is concentrated at different locations. Is there a difference between film cast PTFE and extruded PTFE? The answer is yes. When you film cast PTFE, or in general, when you apply orientation, PTFE is very sensitive to DDR, or drawdown ratio, that is applied. And that's because the molecules, they can orient easily. So if you compare, like in this graph, you can see a low DDR, low drawdown ratio versus a high drawdown ratio, PTFE. The, the, the tube that is produced, let's say we are using RAM extrusion for producing the tube. The tube that is produced with a high DDR has significantly higher mechanical properties compared to a low DDR PTFE, and it's basically has better, mechanical strength. FEP, in the other hand, is not that sensitive to orientation. It's not like PTFE, and the reason for that is the crystalline structure. The disruption that the copolymer bring to the molecules in crystallinity and crystallization, that would decrease the effect of orientation in making the crystalline shape. So the effect of PTFE is more significant. And when you do film casting, the effect of orientation is pretty low. So you basically applying a very low DDR. So it's comparable to a RAM extrusion of PTFE, but at lower DDR. We explained that PTFE is sensitive to orientation. It's highly crystalline, and because of that property, when PTFE is stretched, those crystalline structure, they can create like a island shape, and then with further stretching, a structure is formed called fibrillar structure with a crystal lamina in between, and this would create a porous structure that would make the PTFE porous, and that's why it's called ePTFE. So it's expanded PTFE because now you have voids and pores in between of these crystal lamella. And still, because of those fibrillar structure that you have, a crystal fibril crystal that you have in the middle, the structure is pretty strong and it will hold the whole shape. The other way to make ePTFE is using electrospinning. That's a different method. So basically you electrospin a solution of PTFE and you create knot and fibrils together, and you could have different shape, depending the viscosity and the conditions that process conditions that you apply during the electrospinning. So this porous structure that is created within the PTFE, it's a very good area for the cells to grow. So it's one of the good application of PTFE is vascular bypass grafts because of the tissue ingrowth and healing. It's hydrophobic, it's repelling water, but at the same time is permeable to liquid, and that's a very important property. In analytical polymers, we provide very unique services for biomedical industry. We are able to do full catheter analysis. So we are able to identify the layers, characterize the additives, what additive is used, what is on the surface, what is used as a tie layer, and also the type of polymers. We can identify what kind of polyurethane or PBACs have been used, and then we will help you to choose your right material for the right application. Another services that we do is measuring solvent residual in film cast parts. In some cases, we are producing part by film casting. So in opposite to extrusion, that we melt the polymer and we extrude them, in film casting, we dissolve the polymer in a solvent. Like for example, PBACs is dissolved in a Kersol solvent, or polyurethane is solved in a DMAX solution, depending on the application. And there is a chance that, depending on the process that you apply, some of these solvent will not evaporate from your part and would get trapped in the part. So we have techniques developed to determine if the part has some trapped residual solvent in it or not. We can also provide tensile testing. We can do thermal analysis, thermal degradation analysis. We can do accelerate aging, simulating in vivo conditions, calculating shelf life, and other analytical testing based on your need.